Mm. Hello everyone. So in last lecture we discussed about the behavior of pure inductive, pure capacitive and pure resistive load with the AC supply. Now in this lecture we discuss series combination of RC, resistance and capacitance, and resistance and inductance in the series with the AC supply. So see here, this is the basic circuit of R and L in which resistance is connected and second one is the inductor is connected here. And the voltage across this resistance is VR and the voltage across the inductance is VL. And the supply voltage is AC, which is Vm sine omega t, in which Vm is maximum voltage. So see, this is the circuit. As you know that the resistance is having voltage and current is in phase. So both are in the same phase. Whereas in inductor, what happened? Voltage is leading and current is lagged by 90 degree. So see here, VL and I, there is a phase difference of 90 degree across the inductor. Clear? So see, when we draw the phasor diagram for this circuit, RL circuit, what we will get? We will get the voltage triangle like this. This is the VR. It is in the same phase of I and it is the VL. This is directly leading 90 degree from the I. So these are the two voltage are present in the circuit and the combination of this two voltage or the vector sum of this VR and VL give the total voltage or total supply voltage. So see, when you add these two phasor, what we will get? We will get a resultant voltage VL and VR. So this is nothing but supplied voltage and this is the total voltage you supplied. So this is the main voltage, V supply voltage, and this is the current. See, this is the voltage and this is the current and the angle between them is now phi. If your circuit is only having the inductance, then it means your phasor diagram having the 90 degree phase difference. But now this circuit is having resistance as well as inductance. Due to the presence of this resistance, what happened? The angle is not exactly 90 degree in between voltage and current. Now there is a phase difference of less than 19. So here we assume phi, which is less than 90. Now, as per the waveform, you also know that this is the voltage waveform for the pure inductive circuit. Suppose pure inductive circuit. Now, current is 90 degree lag. It means like this. This is for pure inductance. Now, resistance is add. What happened? The angle is somewhat less than 90 degree. That is phi. Now the waveform is not exactly lag behind by 90 degree from the voltage. Clear? So this is the basic thing about the RL circuit. Now there are some calculations for the RL circuit. Here you see the total voltage, the total supplied voltage is equal to the vector sum of VR square plus VL square give the supplied voltage. And it is the angular velocity from which your vector is rotating. Now VR is I multiplied by R because it is series circuit and current is common. So VR is I into R, whereas VL is I into XL. XL is 2 pi FL. So this is VL and this is VR. So see here, IR square plus IXL square. We write in place of VL and VR. So take I as a common. So here we write I. Only remaining thing in the under root is R square plus XL square. So this quantity is represented as impedance Z. This quantity is impedance of the circuit. So the formula for the impedance is Z square is equal to R square plus XL square. Okay, so this is the impedance. Now what happened? We have to find this angle. So how can we find? So by applying the property of trigonometry, so tan phi is equal to perpendicular upon base. So here perpendicular in the form of voltage is VL divided by VR. So see, VL divided by VR. For this particular triangle, this is also having the same height as a VL. So VL by VR. So after that, we can calculate phi is equal to tan inverse VL by VR. Clear? Now see here, this is the Z. It is also represented in this rectangular form. So see here, R plus JXL. And it is also represented in terms of polar. Polar means Z angle of phi. Now what is Z here? Z is like this, R square plus X square under root. This is the Z and this is the phi. So this is the tan phi is in term of, it is in the term of impedances and the resistance. So this is tan phi, this is impedance. This is impedance shown in the polar form and it is in the rectangular form. So here generally we take voltage as a reference quantity. With respect to voltage, we draw phasor diagram all the quantities. So here I is equal to V by Z. If Z is having any angle, see here we take V as a reference. So V is having at the 0 angle. Now Z is having some angle phi. So I is having the angle of minus phi because phi is going at the numerator side. So V by Z minus of phi. So you can draw like this phi and this is V for the RL circuit. As per the from previous slide, now we all know that V is equal to Vm sin omega t and I is now lag behind the voltage by angle alpha in case of RL circuit. So in case of RL circuit, the angle is less than 90. So here we can represent our I is equal to I maximum sin omega t minus phi. Clear? And this is the value of maximum current Vm by Z. Now there are 3 types of cases from which we can draw a triangle: voltage based, impedance based and power based. So all these 3 triangles are known as voltage triangle for RL circuit, impedance triangle for RL circuit and power triangle for RL circuit. Here you see that this is the voltage triangle in which we take all the quantity of voltage. So VR is what? VR is, sorry, total supply voltage is what? VR square plus VL square. So we represent this VR, that is in phase of the current, and VL is 90° ahead. So that's why it is a vertical component. So this is VL is equal to I multiplied by XL, and the vector sum of both VL and VR give the total voltage V. So here V is equal to I into Z, and you know that Z is nothing but R square plus XL square under root. So see, if I put in place of VR, IR square plus IXL square, here I we take as a common, and R square plus X square, it is replaced by Z. So it is impedance. The unit of XL is in ohm, whereas unit of Z is in ohm. So this is the voltage triangle. Now this is the impedance triangle. See here, this is the impedance triangle, in which we also write like this: R, inductive reactance, and impedance, and we directly write like this two formula, and we also write a formula for phi. So from here you see this is the phi. Phi is what? This XL divided by R for the tan phi. Okay, if you want to find out the phi, take the tan inverse and XL by R. Now here very important thing is power triangle. When you have in your circuit resistance, inductance, and capacitance in your circuit, you have three type of power in your circuit. One is real power, another one is reactive power, and another one is apparent power. You all know that R is dissipating energy in the form of heat. So resistance is not storing any type of energy. Resistance is not storing any type of energy, whereas inductance and capacitance both are storing element. Both are storing element. Inductor store its energy in the form of current in magnetic field, whereas capacitor store the energy in the form of charge in electrostatic field. The magnitude of energy in the inductor is EL is equal to half Li square, whereas energy for capacitor is half CV square. So this is the representation of energy which is stored by the inductor. As you supplied this inductor and capacitor with the AC, so both inductor and capacitor store or taking the energy in one cycle and giving back to the source in the next cycle. Okay, so in first cycle they are taking the energy, and in second cycle they giving the energy to the source. So they are not consuming any type of power. Okay, so inductor and capacitor is not consuming any power, whereas the resistance is consuming the power. That's why the power across resistance is real power, active power, or effective power. So these are the different name of this real power. So see, the representation of the real or active power is I square R, and it is also represented as P is equal to VI cos phi. So here you see in the diagram, this is P, real power across the resistance. This is the reactive power, I square into XL. This is the reactive power due to the presence of inductance, and it is represented by Q. And this is apparent power, total power supplied to the circuit. This is the total power supplied to the circuit, and it is the power which is actually consumed by the resistance, and it is the power which is only circulate in the circuit. This reactive power is not do any useful or fruitful in the circuit. It is only rotate in the circuit. So this is reactive power. Reactive power is equal to Q is equal to VI sin phi. So here we also represented as a I square multiplied by XL. And here apparent power is S is equal to VI equal to I square into Z. This is the total power supplied to the circuit, and this total power is divided into again two parts, P and Q, active and reactive power. So S is equal to P square plus Q square, or in other words, S square equal to P square and Q square. So this is the resultant total power, P square plus Q square. So these are the three cases for the AC through RL. Now calculation of instantaneous power. Now we all know that V multiplied by I, small v and small I represent the instantaneous power. So V is equal to Vm sin omega t multiplied by Im sin omega t minus phi. So this is Vm Im sin omega t multiplied by sin omega t minus phi. So when you combine this, so we multiplied by 2 here and divided by the 2. So what you have here, you have a one more identity is sin A into sin B. So when you solve this identity, you will get this cos phi minus cos 2 omega t minus phi. So this is the after solution. Okay. Now you here one thing you observe that the two component of power is having Vm Im by 2 cos phi and minus Vm Im by 2 cos 2 omega t minus phi. These are the two component in the power. Now this component is also represented as VR in terms of VRMS. VRMS is nothing but Vm by root 2, whereas IRMS is equal to Im by root 2. So V multiplied by I multiplied by cos phi divided by 2 minus, now this term V I cos 2 omega t minus phi upon, not upon 2 is replaced by RMS value. So Vi cos 2 omega t minus 5. So the second component is having just the double of the frequency. That's why this average power or this power is equal to 0 during the, suppose this is the voltage and voltage waveform, but the waveform of power in during this is like this. Because of this, 2 is multiplied by omega t. That's why the power is not included in the calculation, this power. Okay. So the only instantaneous power is considered as PT is equal to Vm Im cos phi upon 2 or Vi cos phi. This term is equal to 0 because of the double of the supplied frequency, or it has the just twice frequency of the voltage and or current. Now this is the average power calculation. Now average power is calculated by the from 0 to 2 pi, or 0 to 2 pi. Here I have to rub this. Now here you see that 0 to 2 pi, you have to take the power. The limit is for 0 to 2 pi. So 0 to 2 pi Vm Im divided by 2, and we take directly this formula from here because after solving this we will get this only. So here directly cos phi minus cos 2 omega t minus phi d omega t. This is the instantaneous power we take here. Now this term is constant Vm Im by 2, so we take it out here. Now half and 0 to 2 pi cos phi minus cos 2 omega t minus phi bracket close. Now here when you solve or open the integration, what you will get? You will get the cos omega t phi and cos 2 omega t minus phi integration from 0 to 2 pi. Here Vm by 4 pi integration for it, and this is the integration. Now we will get what we will get. We will get, after solving this, we will get this average power Vm Im by 2 into cos phi, and we replace this Vm Im by 2 into a RMS value. So after putting the RMS value, we will get Vi cos phi. So this is the value of average power Vi cos phi. So this is the representation of the waveform for RL circuit. This is V, and this is the phi angle which is lag behind by the voltage, and this is the waveform for current, and it is representation is Im sin omega t minus phi. And this is the power, instantaneous power. This is the instantaneous power. Now these are the some important formula. So the vector sum of V is equal to VR plus VL, where VR is I into R, VL is I into JXL. Now J is the component which we discussed in our previous lecture, J multiplied by X, and this is the V is equal to I R plus JXL, and R plus JXL is what? Is equal to Z. So from here you take this Z. We also write like this, V is equal to IZ. So I is equal to V divided by R plus JXL. Also it is equal to V by Z. XL is equal to omega L 2 pi FL, and where you can also write like this, V divided by R plus J omega L, because XL is omega L. Okay. Now this is the complex representation of impedance. This is the complex representation of the voltage. So here Z is equal to R plus j omega L, and in the uh, Cartesian form we have I is equal to V by R plus j omega L. If you multiply by R minus j omega L and R minus j omega L, multiply and divide into numerator and denominator, so you will get I is in the form of this formula. Okay, so we multiplied by R divided by R square plus omega square L square minus j V omega L divided by R square plus omega square into L square. So here minus j indicate that the current is lag behind the voltage. So what it indicate? The current is lag behind the voltage. Now complex impedance, as you know, Z is equal to R plus j omega L, and Cartesian form is I is equal to V by R square plus omega square L square minus j V omega L divided by R square plus omega square L. This is our Cartesian form. Now, if you want to calculate in the polar form, because sometime when you solve the numerical, you also need your impedance in the polar form. So at some time you have to convert your formula by using the formula in the polar form. So I is equal to V by R square omega square into L square. This is our basic formula. You know that V by Z, if Z is having this, so we can write like this. Okay, so this is the representation, and here phi is what? We already know that tan inverse of omega L by R, or in other form you also write like this, tan inverse XL by R. So minus phi L is what? Minus phi L is nothing. It indicates the current is lagging. So see, this is the V and this is the total, this is the current. So see the angle in between supplied voltage and supplied current, because as the circuit is in series, so current is I only. So here the angle is phi L. This is the voltage across resistance, which is in the phase of current, and this is the voltage across inductance, which is 90-degree lead from the current. So this is I is equal to V upon Z. You also represent like this in the form of magnitude. So take the mod of I here, so you will get the current I. Okay, now cos phi. Cos phi you also calculate here. You see that this is the phi L. So phi L is nothing but tan inverse of omega L by R. So you, for calculating the phi L, you multiply both the side by the cos. So you will get cos phi. Cos phi is the power factor, and we discuss it will later also. Now the complex impedance is this R plus j omega L, and this is the magnitude of the impedance is under root R square plus omega square multiplied by L square, or R square plus XL ka square. So this is the triangle also. This is R. This is the vertical component. J omega L is equal to JXL, and it is the resultant R square plus omega square L square equal to Z. So this is the numerical based on the RL circuit. So see, in this numerical, we have a resistance. A resistance of 7.0 ohm is connected in series with the pure inductance of 31.8 millihenry, and the circuit is connected to a 100 volt 50 hertz sinusoidal supply. Now calculate circuit current, phase angle. Now, as per the numerical given, resistance is having 7 ohm. So this is 7 ohm resistance and inductance of 31.8 millihenry. Milli means 10 to the power minus 3. So L is equal to 31.8 millihenry is given. And the supply voltage is 100 volt. So it is 100 volt. And frequency of the supply is 50 hertz. Now they want us is circuit current I and the phase angle. They require these two things we have to find. So first of all, XL is 2 pi FL. So 2 pi, frequency is 50 and L is given 31.8 and milli, it means 10 to the power minus 3. So when you solve this, you will get 10. Okay. Now in next, Z is equal to, we know that R square plus XL square under root. R is having the value of 7 square, 10 square divided by, sorry, under root, take the under root of, so it will give Z. So Z is coming on solving this 12.2 ohm. Now for finding the circuit current, I is equal to V by Z. V is given 100. So this is V and Z we calculated 12.2. So I is equal to 8.2 ampere. Now we have to find phi. Phi is equal to tan inverse of XL by R. This is the one of the formula. And XL we have equal to 10. From here you take, and R we have 7. So 10 by 7, you will get 55.1 is the phi. Now in the second numerical, see here two equations are given for a circuit having pure resistance and pure inductance in it. So this is the circuit is given as per the numerical. The series circuit containing pure resistance and pure inductance. The current and the voltage are expressed as. So current is given, I is equal to 5 sine 314t plus 2 pi by 3. This is the current, and voltage is 15 sine 314t plus 5 pi by 6. This is the given voltage in the equation. Now they are they ask what is the impedance of the circuit and what is the value of resistance. So number 1, impedance you have to find. Number 2, you have to find resistance, value of resistance. Number 3, they want inductance in Henry. So we have to find L. And what is the average power drawn by the circuit? So power P average and power factor 5. So these are the 5 quantity we have to find. So first of all, here you take by the equation IT equal to 5 sine 314t plus 2 pi by 3. From here we calculate the angle. So 2 pi by 3. So 2 pi by 3 means 2 pi by 3 means 2 multiplied by 180. Sorry, 180 divided by 3. What you will get? We will get 120. So our angle is, okay, it is into 120 degree. Now for 5 pi by 6 means 5 pi by 6 means 5 multiplied by 180 divided by 6. So in place of pi you have to write 180. So you will get the angle of 150. It means that if you have an reference, suppose this is x-axis, so your current is at 120° ahead from this. Okay. So this is your value of angle of your current. So the angle between voltage and current is 150 minus 120. This is 30°. The angle between voltage and current is subtraction from 150 to 120. Okay. So this is the 30°. Okay. Now, first of all, we have to find Z. Z is what? Vm by Im. This is the way we can find the Z. Vm is what? You know that this is the equation Vm sin omega t. So this 15 is nothing but Vm. And what is Im? Im sin omega t. So this is Im. So 15 by 5, you will get 3 ohm. So Z is equal to 3 ohm. Now for finding the power, resistance, we have to first of all find the power. So here I calculate the power VI cos phi. Okay. You also calculate from this Vm by root 2, Im by, because Vm and Im are directly given into cos phi. Here phi is what? Phi is 30°. Phi, the difference between voltage and current is 30. This is nothing but the phi. So you also calculate it from this. So here Vm is 15 divided by root 2 multiplied by 5 divided by root 2 into cos phi 30 is equal to P average. So when you solve it, so you will get P average is 5.784. So P average we also find. Now we know that P average, here P is equal to V square by R. We know the V RMS and the P. From here we also know the P. So 5.78 is equal to VRMS is what? From here we can calculate the VRMS. VRMS is nothing but Vm by root 2. So Vm by root 2 means Vm is, here see Vm is 15. So 15 by root 2. So 15 by root 2 gives 10.608. So 10.608 square divided by R. From here you will find out the R. R is equal to 19.4 ohm. Now Z, you know that Z is having this formula R square plus XL square under root. So R we having, R we have, Z we have. Now we have to find XL to find the value of L. So here we open this under root and Z 3 square minus 19.45 square is give the XL square. So from here we will get, this is the XL. Now XL is nothing but 2 pi FL. So from here you can calculate XL divided by 2 pi F. F is what? F is 50 Hertz and X is 19.2. So 19.2 divided by 2 pi multiplied by 50 is the value of inductance. So this is the numerical. Now next numerical is, now see what they ask. Two coils A and B are connected in series. Two coils. Two coils means one inductance with one resistance is making a one coil. If you have two coil, it means two separate inductance and two separate resistance. The resistance of A is 5 ohm and the inductance of B is 0.015 Henry. If the input from the supply is 3 kilowatt and 2 kVAR, find the inductance of A and the resistance of B. Calculate the voltage across each coil. It means your circuit is having resistance and inductance, then resistance and inductance. This is the two coils. This is coil A. This is coil B. And it is supplied by a AC source having the value of 240 volt. Now here you see that A is having the resistance of 5 ohm, whereas B is having the inductance of 0.015 Henry. Okay, the input from the supply is 3 kilowatt. It means power is given to you. So power is 3 kilowatt. And 2 kVAR. kVAR means reactive power. So the reactive power Q, power across the inductor, is also given, that is 2 kVAR. Okay. So these are the given quantity. As you know that apparent power S square is equal to P square plus Q square. So we have P and Q. So you will calculate from here apparent power. So see here, this is the 3 kVAR plus 2 kVAR. So this is P and this is Q. So we will get total apparent power 3.606 kVA. This is the apparent power. Now circuit current. So total power divided by, see here, power is equal to, in the form of V into I. So V into I is equal to 3.606 divided by voltage. Voltage is given 240. So here you divide your input voltage. So V and P cancel. So we will get the current. So see, from here we will get the current 15.03 ampere. So this is the 15.3 ampere in the circuit. So this is 15.03 ampere current. Now total current I square RA plus RB. Now this will give what? Give active power, and active power already given, that is 3 kilowatt. And how you identify this is active power? Because of its unit kW. So now this is 3000. See here. So it will give the equation RA plus RB equal to 13.3 ohm. Now RA plus RB equal to 13.3 ohm and RA is given. So put the value of RA is equal to 5. So what we have? 5 plus RB is equal to 13.3. So RB is equal to 8.3 ohm. So in this way, here the resistance of coil B is calculated. Now we have to calculate the inductance of coil A. See now, XA plus XB. XA plus XB square. 1 second. I have to rub this. I have to write this formula like this. Z is equal to RA plus RB, the complete impedance. Z. RA plus RB square plus XA plus XB square divided by, under root of both will give impedance. Okay. And here, what is the value of impedance? Impedance is total voltage and total current. Total voltage is 240 is given, and total current we found is, see here, 15.3. This is the circuit current, 15.3. So divided by 15.3, we will get 15.97 is our overall impedance. Now Z is 15.97 minus, we know what is RA and RB. So we have the value of RA and RB. So it is 13.3 square. Z square is equal to XA plus XB. XB is given. This is what? This is XB. So XB is 0.015. So this is the equation. This is the equation. Okay. So from this equation, we can calculate XA. So after solving this equation, you will get the value of XA is 4.13. This is XA. Okay. So now you find ZA and ZB separately. Okay. So see, ZA is what? ZA is a combination of 5 ohm resistance and reactance of coil A, that is 4.13. So 5 square plus 4.13 square is equal to Z square. From this equation, you can find ZA, and from this equation, RB. What is RB? RB is having the value of 8.3. See here in this diagram, this is the 8.3. So 8.3 ka square plus what is XB? XB is given 0.015 ka square, and this is square. So from this you find ZB. So what is the ZA after solving it? So ZA is nothing but 6.585 here, and ZB is 9.545. So this is ZB. So unit is in ohm. Now you can find drop across each coil. So what is the drop across each coil? Drop across each coil is I into ZA is equal to, I is what? 15.03 multiplied by ZA. ZA is 6.585. 6.585, and I into ZB. ZB is equal to, again, I into 0 multiplied by 9.545. 9.545. So it will give the I into ZA and I into ZB. So this is 97.5 and this is 143 point. So this is your complete numerical. Now this is one more numerical here. A coil having a resistance of 10 ohm and an inductance of 40 millihenry is connected to a 200 volt 50 hertz supply. Calculate the impedance of coil, current, power factor and power consumed. So coil is having 10 ohm resistance, 40 millihenry inductance, supply of 200 volt and 50 hertz. What we have to find? Impedance, current, power factor, cos phi and power consumed. So these 4 quantity we have to find. So first of all, we have to find the Z. For finding the Z, we require R square plus XL square. So we require R and XL. For finding the XL, we have one formula 2 pi FL. L is what? 40 multiplied by 10 to the power minus 3. It is in the millihenry. So after putting the value of L here and F is 50 is given. So put L here and F is the 50. So we will get 12.57 is the XL. After getting the XL, you write here in the form of complex impedance 10 plus J 12.57. This is the XL, R plus J XL. So see, it convert it into the polar form. So how this 16.06 come? The 16.06 come is like this. 10 square plus 12.57 square gives the 16.06 ohm. So this is 16.06. You write directly here. And how you can find this angle? So phi is equal to tan inverse of what is XL? XL is 12.57 divided by R. XL by R. So it will give the angle of 51.5 degree. So this is the representation of Z in the polar form. So here Z we find. Now what is I? I is equal to supplied voltage divided by total impedance. So I is equal to V by Z. So V is given 200 and Z is what? 16.06 and angle kya hai? 15.5. So 200 divided by 16.06 gives the 12.45 and angle 51.5. So now power factor is equal to cos phi and it is cos of 51.5 is equal to 0.62 lagging. And the total power is equal to VI cos phi. So V is 200 volt. Current is 12.45 and cos phi is 0.62. So this is the total power which is coming after the solving is 2 kilowatt. Now this is the numerical for you as an assignment. I also give the hint in this numerical. So it is to take this for the practice and here answers are also mentioned. Now the second case is AC through RC circuit. RC circuit is nothing but the combination of R and C. See here, the R is connected and the C is connected here. This is the VR voltage across resistance and this is the VC voltage across the capacitance. And this is the supply voltage. Instantaneous voltage is equal to Vm sin omega t. So this is the circuit representation. And we know that in case of resistance, voltage and current both are in the same phase. So see, this is. Now in the case of capacitor, voltage is leading and voltage is lagging and current is leading. So this is current and this is V. So if V is the reference, so current is like this. So this is I. So see here, this is the current and this is the voltage. So in case of capacitor, the phasor diagram is follow like this. So the voltage triangle you can make like this. This is the VR, voltage across resistance, which is in the same phase with the resistance. And this is the voltage, which is 90 degree lag behind the supply current. So it is here. This is of VC. If you make the resultant voltage, this is the V. Okay. So here you see that the waveform of the capacitance and resistance combination circuit. Now, in case of pure capacitance, what happened? In case of pure capacitance, the angle between voltage and current is 90 degrees. Okay, this is I and this is V. But when you connected a resistance in series with the capacitance, now the angle between current and voltage is no more 90 degree. It is somewhat less than the 90 degree. So it is like this. So in the waveform, here you see, suppose this is the voltage waveform. Green one is the voltage waveform. When I want to draw a current, so current is now leading by some angle phi. So see, it is start earlier than the voltage. So see, this is the current, and the representation of current equation is Im sin omega t plus phi, whereas voltage is Vm sin omega t. But here some angle is in addition with the current because of its leading nature, or it is having the leading phase difference. So this is the vector sum of the voltage across capacitor and resistor. So voltage sum of VR and VC gives the total supply voltage. So see here, VR square plus, here you take minus of VC because it is in the fourth quadrant. So see, we represent VR by I into R, and VC is equal to I into XC. So you write here in place of VR and VC. So what you will get? R square and XC square, and take this common parameter outside from the under root. Okay, so only remaining is R square plus XC square. Now this R square plus XC square is nothing but it is the impedance of the circuit. So sometimes it is equivalent like this. So this is the impedance of the circuit. So I in any RC circuit is, this is V, this is I. So I is equal to what? V by Z. So V by Z. Okay, and the combination of Z is this. Impedance is in ohm, and Z is also represented by R square plus XC ka square. Whereas tan phi, from here you can find the tan phi. Tan phi is equal to VC by VR, or in other thing XC by R also. If you multiplied it by I, then I cancel. So it is also XC by R. So it clearly shows that in RC circuit, the current is leading by angle phi. So the representation of current is Im sin omega t plus phi, whereas the representation of voltage is Vm sin omega t. So you also represent power factor is equal to R by Z. Cos phi is equal to R by Z. And also P by S. P is equal to what? Vi cos phi, and S is equal to Vi. So Vi cancel. It will give the cos phi. Clear? Now instantaneous power. Again, we multiplied it with the instantaneous voltage and instantaneous current. Here Write down the formula of instantaneous voltage and current, Vm sin omega t, Im sin omega t. So see here, Vm Im sin omega t multiplied by sin omega t plus phi. Now what happened? Multiplied and divided by the 2. So you will get this equation. This is the total instantaneous power across the RC series circuit. So Vm Im by 2 multiplied by cos phi minus cos 2 omega t plus phi. Now the average, for calculating the average, we here directly take the equation for 0 to pi. So Vm Im 2 be divided by 2 cos phi minus cos 2 omega t plus phi and d omega t. Actually here 1 by 2 pi is missing. So now this is the equation for the average power. So Vm Im by 2 pi is as it is here. Now integrate with this equation and Vm Im 4 pi and integration of this equation. So after integration and solving and putting the limits 0 to 2 pi, what you will get? You will get the equation for P averages Vm Im by 2 multiplied by cos phi. So Vm Im by 2 cos phi. Again you separate it Vm by root 2 and Im by root 2. So both are equal to the RMS value of voltage and RMS value of current multiplied by cos phi. So power is nothing but Vi cos phi, and I earlier explained that why the second component is 0, because it has the twice of the frequency. Now there are 3 cases in RC circuit also. We have voltage triangle, impedance triangle and power triangle. In voltage triangle, what we have? The VR voltage in phase with current, VC voltage which is lag by current, 90-degree lag current, and the combination of this VR and VC give the resultant voltage. So VR is equal to I into R, VC is equal to I into minus XC, and V equal to I into Z. So here you write like this: V is equal to VR square plus VC square divided by, not divided by, under root of IR square plus IXC square. From here you take it out this common I, and this term is nothing but it is impedance. Now second thing is impedance triangle. You also draw R component. See, it is always in phase with the current. This is the XC component. This is always leading with the current. So this is a vertical component here, and this is the Z. So see, Z. And you can find phi from here. Phi is what? XC by R. You also write draw a power triangle. So power triangle in terms of all the power. When you multiplied your real power, when you have a current and you multiplied it with the R, then it is the real power. It is the real power. Here I square XL, it is the reactive power, and apparent power is nothing but it is the I square by Z. So these are the 3 power present in the circuit. So see, this is the real power I square R, reactive power Vi sin phi. If you split the component, so Q is equal to Vi sin phi or I square into XL, and apparent power is V multiplied by I square into Z. So S is equal to P square plus Q square. So apparent power unit is volt ampere, active power unit is watt, and reactive power unit is VAR. And the formula for phi is tan inverse of Q upon P, means reactive power by active Now this is the revision part. See, total voltage is the summation of VC plus VR. VR is I into resistance. VC, voltage across capacitance, is I into, in the form of JXC. So you can represent total V is equal to I multiplied by impedance I into Z. So Z is equal to R minus JXC. You also write the equation for I is equal to V divided by R minus JXC. So this is the equation for I. XC is nothing but 1 upon omega C is equal to 1 by 2 pi FC. I is equal to, so now you can write V divided by R minus J. In place of XC, you write 1 by omega C. So you here J is as it is and 1 by omega C you write here. So this is again a formula for current, and this is Z. Z is also write like this, XC, and in place of XC you can write 1 upon omega C. So the current in the Cartesian form you also represent like this. I is equal to V multiplied by R divided by R square plus 1 by omega square C square plus J, V divided by omega C and divided by R square plus 1 upon omega square multiplied by C square. So this is the one more formula for the current. You can directly calculate it from this, and plus J here represent that current is leading. So this is the main thing, current is leading. Now see here, this is the complex form of the impedance representation, R minus J by omega C. Whereas in Cartesian form, we already derived it, V multiplied by R and so on. So in polar form, you have to write magnitude with the angle. So how you can find the magnitude? Magnitude is nothing but the V divided by R square plus 1 upon omega square multiplied by C square is the magnitude of the current. Whereas you can find the phi C from this formula, tan inverse of 1 upon omega C R. So this is the, if you want to find the cos phi, so multiplied it with cos, and here you also multiplied it with cos, so you will get your cos phi. See the diagram, this is the supply voltage V, and this is the current. Due to the presence of capacitance, now current is leading. So the voltage across resistance is in phase with the current. So see, this is the I. And now the voltage across the capacitor is 90-degree lag behind the current. So this is VC. Okay. So this is the voltage and this is the current. Okay. And the angle in between voltage and current is phi C. Now this is the one numerical is given. There are 4 to 5 numericals are given. So see here in this case, we have a capacitor of 8.0 microfarad takes a current of 1.0 ampere. When the alternating voltage applied across it is the 230 volt. Calculate frequency of the applied voltage, resistance to be connected in series with the capacitor to reduce the current in the circuit to 0.5 ampere at the same frequency, and the phase angle of the resulting circuit. So first thing we have to calculate frequency. Number second, the resistance to be connected in series with the capacitor, value of R. Okay. So the current should be reduced by 0.5 ampere. So how much resistance you require in your circuit? So the current is only 0.5 ampere. And the last one is the phase angle, that is pi. So first of all, for finding the frequency, we have to find Xc. Xc is V by I. V by I is the Xc. So here 230 is given and I is 1.0. Okay. So this is 230 ohm is the Xc. From here, you can directly calculate 230 divided by 1 is equal to 230 ohm. Now Xc is what? Xc is 1 upon 2 pi Fc. The value of C is already given, 8 microfarad. 8 microfarad means, micro means 10 to the power minus 6. So 1 upon 2 pi, F is the 50. Sorry, F we have to find, and F is not given, multiplied by 8 to 10 to the power minus 6 is equal to 230. So here we have to find F. What you have to find? F. So by using this equation, we have to find F. So after applying this formula, we will get F is equal to 86.5 Hertz. Now, second case is, what is the value of resistance in series with the capacitor? Then the capacitor, the circuit will take the 0.5 ampere current. Okay. So in that case, your circuit should take the 0.5 ampere current. So here current value is 0.5 ampere is given. So 230 divided by 0.5 is equal to 460 ohm. This is nothing but the impedance. Okay. And we know that Xc is already, we know, 230 ohm. So by the identity of Z is equal to R square plus Xc square under root, you will find the value of R. So R is Z square minus Xc square is equal to R under root. So you will get R is 398 ohm here. Now for finding the phi, phi is equal to cos inverse of R by Z. We know the value of R, 398, and the Z is 460. So cos inverse of 398 divided by 460 will give the 30 degree. So this is the numerical. There are various numerical. So I take this. So here in this circuit, circuit is having, this circuit consume 2000 watt and 0.5 leading power factor. Okay, it means your circuit is having capacitor in it. Okay, when connected to 230 volt 50 hertz AC supply, so your circuit is having leading power factor. It means it is having this type of combination. Okay, and the supply voltage is 230 volt is given, 50 hertz is frequency, and it consumes power is given 2000 watt. It means it is I square R is 2000 watt, or in other word, VI cos phi is equal to 2000 watt. All are same. It is given, and power factor phi is what? Cos phi is equal to 0.5 is given. Now you see that the VI cos phi is given 230, and voltage is also given 230 volts. You see, and cos phi is given 0.5. So from here we can calculate I. Now First of all, we have to calculate kVA, means apparent power, and kVAR means Q. Now from here, as having the formula of V multiplied by I. So you also having the value of power. Power is given 2000 to 2000 divided by cos phi is given 0.5 is equal to 4 kVA. So 4 kVA is nothing but the apparent power. Now the reactive power you can calculate like this, VI sin phi. Now from here from cos phi is given. So cos phi is equal to 0.5. So phi is equal to cos inverse of 0.5. It will give 60 degree. So you write here 230 is the voltage. Current we found from this equation 17.39. So this is the 17.39, as this is sin 60 is equal to 3.464 kVA. So this is the reactive power. So in this way, you can calculate the active reactive power also in the circuit. And this numerical is for you for the practice. So in next case, here we discuss general about the reactive power and the active power and apparent power. Apparent power is nothing but the total power given to the circuit from the source. So suppose this is source, so supply voltage into supply current is the total power. One second. So this is the apparent power V into I, and its unit is VA. Whereas the active power is the power dissipated across resistance I square R. This is also represented as VI cos phi. Its unit is in watt. And reactive power, I already mentioned that this power is having no useful work in the circuit. It only circulate in the circuit. And this is represented by Q, and it is across inductance and capacitance. So it is represented by either I square XL or I square XC. So see, it is also represented as I into X into sin phi or VI sin phi. The unit of reactive power is volt ampere reactive, VAR. So S is equal to P square plus Q square. This is a power triangle in which the reactive power, real power, reactive power, and the combination of both real and reactive is apparent power. So the phi is equal to Q by P. So here you can find phi is equal to tan inverse of Q by P. Now another component, very important component, is come into the picture, that is power factor. Power factor is basically we define as the cosine angle between applied voltage and the resultant current, but it has, or it is the measure of how much effective power you utilize in your circuit from the overall power. So it shows the effective utilization of effective power from the total power, and it is defined as a active power divided by apparent power. So apparent power is the total power, whereas the active power is the actually utilized power or effective power. So see here, this is the voltage, this is the P VI cos phi, this is the reactive power Q VI sin phi, and its resultant power is VI. So this is the angle phi. Okay, this is the angle phi. So this represents the cos phi. So in this way, here we finished our lecture for the RL and RC network in series. In next lecture, we will discuss RLC series and RLC parallel circuit. So thank you to all.